governs its motion. What goes up must come down. With an old saying, man has unconsciously tried to sum up a basic force in his universe. This force is one of the most familiar things in the world, yet nothing has puzzled scientists more. Despite all their study, it is still a mystery. It is known as gravitation. Man has long known how to use gravitation. He has also learned recently to overcome it. But he still asks the same kind of questions that he asked thousands of years ago. What is gravitation? Why does it act the way it does? Man's wondering about such things has inspired many theories about the world around him. Ancient civilizations looked for order and harmony throughout the cosmos. According to the Egyptians, the goddess of the heavens arched her body like a canopy over the earth, holding up the stars, the planets, and the sun, and letting them glide over her back once each day. In one Greek cosmos, a large earth was surrounded by concentric spheres, which carried the moon, the sun, the other planets, and the stars around it every 24 hours. Within this universe, 4 elements fell naturally in place. Earth, the heaviest at the bottom. Water, not so heavy on top of it. Then air, much lighter. And then fire, lightest of all, high above everything. Weight was important in this cosmos. The Greeks were trying to deal with gravitation, although they did not know that such a thing existed. Such a cosmos, with the Earth at its center, appealed to an age whose philosophers believed man to be the center of all things. This neat and logical universe won Aristotle's approval, which helped it remain in favor for nearly 2,000 years. But in the 16th century, the Aristotelian cosmos was successfully challenged by the Polish astronomer Copernicus, who adopted another concept. Here the sun was at the center of things, and the Earth merely one of several planets orbiting around it. This universe was refined nearly a century later by the German astronomer Kepler, who combined the Copernican view with new observations and worked out laws describing rather simply the motions of the planets. Kepler found that each planet follows an elliptical path and travels faster when it is nearer the sun. He also found a simple relationship between the period of a planet's revolution and its distance from the sun. The period squared is proportional to the distance cubed. With this formula, Kepler, without knowing it, provided a clue to the sun's gravitational field. Meanwhile, the Italian Galileo was studying the motions of much nearer objects. One morning in church, his attention was caught by a swinging lamp. Although each swing was smaller than the one before it, the time of each swing was the same. Galileo wondered why. In trying to solve problems like this, he became one of the first to perform practical experiments with motions and forces, and to understand what those experiments implied. Galileo showed that the fall of all bodies toward Earth is independent of any other motion, such as horizontal movement. He also demonstrated that no matter what their size and weight, All falling bodies gain speed at the same rate. He concluded that force is necessary only to change the speed or direction of motion. Galileo's findings led ultimately to an explanation of the motions of all massive objects on Earth. It remained for the 17th century English genius, Sir Isaac Newton, to connect Galileo's experiments, Kepler's equations, and the universe of Copernicus. Newton's view of the physical world gives us the basis for solving practically all our problems in mechanics. For example, his own drawing showed that if a projectile were hurled at greater and greater speeds, it would become a satellite. Newton was the first to state that all motion, whether of projectiles, pendulums, or planets, is subject to the same kind of force acting under different circumstances. In this monumental work, he set forth a universal principle based on his studies of motion. Newton stated that each body of matter in the universe is attracted to every other body. The greater the mass of a body, the greater its attraction. The greater the distance between bodies, the less the attraction. Newton's formula states that the attraction between bodies is proportional to the product of their masses divided by the square of the distance between them. To this fundamental attraction, Newton gave the name gravitation. He also stated that every massive body is held together by self-gravity, the attraction between each of its own particles of matter. Thus, the history of any star, our sun, for example, came to be understood as a vast struggle between equal forces. The fiery energy that tends to blow the mass apart, and the gravitation that holds it together. The balanced, ordered universe described by Newton reigned supreme for more than 2 centuries. And within this classical framework, man began to make sense of more complex motions controlled by gravitation. He learned how to make accurate predictions about the motions of astronomical bodies. These predictions, in turn, led to important discoveries. For example, from various observations, astronomers calculated the orbit of the newly discovered planet Uranus, taking into account the location and gravitational influence of other known planets. But very soon, Uranus was seen to wander slightly from its expected path. Studying the direction, amount, and time of the planet's deviation, astronomers concluded that another body in space must be attracting Uranus. And they were right. In 1846, the body was discovered as predicted, identified as a planet, and given the name Neptune. Since then, Newton's law has helped astronomers understand the structure of galaxies and other great star systems, how they are held together, and how the material in them is distributed. Moreover, with the development of precise instruments and methods of measuring gravity, man has become able to map the distribution of mass on his own planet. In 1798, the English scientist Henry Cavendish, using equipment built like this model, found a way to measure the gravitational attraction between known masses a known distance apart. The amount of attraction exerted by the larger masses on the smaller ones at the end of the torsion balance can be measured by the degree of twist in the suspension fiber. Thus, once man learned that a specific mass exerts a specific amount of attraction, he could calculate the amount of mass in any object by the amount of its attraction. In the last century, man has measured gravitational attraction all over the Earth, and he has used the relation between mass and attraction to interpret his measurements. However, on Earth, These measurements are greatly affected by the fact that our planet is rotating. First of all, the Earth's spin carries an object along much faster at the equator than near the poles. Therefore, the pull of gravity is counteracted more at the equator, and the object there weighs less than an identical object near one of the poles. Furthermore, rotation causes the equatorial zone to bulge and the polar regions to flatten. This brings objects near the poles closer to the Earth's center and places objects at the equator farther away. The difference in weight between the two identical objects is thus even greater. For example, if on a spring scale at the Panama Canal you weigh 193 pounds, in Greenland, even without the extra weight of the boots, you will weigh a pound more. And the bob of a clock pendulum, adjusted to keep perfect time at the poles, will weigh less at the equator and swing more slowly there. Thus, the clock will lose about 10 seconds an hour, about a day a year. Since the period of a pendulum swing depends on gravity, the pendulum is a good instrument for measuring gravitational acceleration. This is usually done by measuring the total elapsed time of a large number of swings. In this way, the absolute value of gravity has been found at stations throughout the world, such as Teddington, England. The figure shown here is derived from the length of a pendulum and the average time taken by its swings. To get such a reliable measurement, the Earth's magnetic field must be nullified. The pendulum must swing in a vacuum chamber, free of air resistance, moisture, and temperature changes that would affect its motion. At a number of stations throughout the world, including the National Bureau of Standards in Washington, scientists are measuring the acceleration of gravity directly. A rod is designed to fall freely in a vacuum inside a tube. Spaced holes in the rod act like a camera shutter, allowing light to pass to a recording device when the apparatus is dropped. The time between flashes is measured to the nearest 10 millionth of a second, providing a direct measure of acceleration. Thus, modern technology refines Galileo's original experiment. Using the pendulum stations as reference points, scientists measure gravitational variations all over the world. Moreover, in the last few decades, they have been able to take measurements in the vast oceans covering nearly 3/4 of our planet. Measuring gravity at sea is more difficult than on land. The acceleration of gravity must be clearly differentiated from the motions of the vessel. This problem was solved in the 1920s by the development of an instrument which used the classical pendulum in a new way. Identical pendulums swing in opposite directions on a supporting frame. The frame is hung on gimbals to reduce the influence of the vessel's roll. The pendulums are swung for about half an hour, and the vessel's accelerations are averaged out. The average acceleration acting on the pendulums is the local value of gravity. Under the best conditions, error in measuring can be reduced to 3 or 4 parts in a million. Gravity can now be measured more quickly and economically from surface ships, due to recent advances in instrumentation. This gravity meter is hung on gimbals, which keep it relatively unaffected by surface rolling and pitching. Other gravity meters are used to make measurements from aircraft and on land. Many of them are portable. All operate on the same basic principle. Gravitation exerts a pull on a weighted arm suspended on a spring. The arm, shown here on a different mount, is connected to a pointer. A measurement is made by adjusting the pointer to 0. How far the knob has to be turned at each location indicates the difference in gravitational pull between that location and the previous one. The spring-balanced gravity meter is so sensitive that it will measure the difference in pull between two adjacent positions, even if one of them is only a few feet closer to the center of the Earth. During the International Geophysical Year, the measurement of gravity was increasingly standardized and extended all over the Earth. A worldwide network of gravity bases was developed. In collecting gravity measurements around the world, scientists often stop only long enough to take the local reading before proceeding to the next point. Sometimes the gravity meter is sent by itself to be met and used by someone stationed at each place. Along with gravity, whether measured on land, at sea, or from aircraft, altitude must be noted so that the gravity reading may later be adjusted to the sea level standard. At gravity research centers such as the University of Wisconsin, data are gathered from all parts of the world. The traverses and findings of the field parties are plotted and compared. Traverses are sometimes made on foot and readings taken very close together. In this way, a detailed gravity portrait of large areas is built up. Taken from notes made in the field, the exact position of each station is used to correct the actual reading for the differences in the Earth's gravity field at different latitudes. Corrections are also made for the tidal pull of the moon, for temperature, and for possible drift of the gravity meter. On this geological map showing rock distribution, corrected gravity readings are plotted in the form of contour lines, indicating local excesses or deficiencies in gravitational pull. The gravitational pattern, when compared with the geological pattern, provides geodesists and seismologists with important clues to the structure of the Earth's crust. Although gravity measurements vary from place to place, the large visible masses do not cause as great a variation as might be expected. This can be explained by the way the Earth's hard crust floats on the plastic mantle underneath. In a normal region where the land is not very high, the crust is generally about 20 miles thick, and only a small fraction of it floats above sea level. In a mountainous region, the crust sinks deeper into the mantle to support the extra weight of the mountains. This deep projection is known as a mountain root. On the other hand, in the oceans, only a thin crust is needed to support the water, which is less than half as heavy as rock. In this ideal picture, all these floating sections have about the same weight and mass. Therefore, they would exert the same pull on a gravity meter. This equalization of masses is called isostasy. Actually, the Earth's crust departs from this ideal picture. Different sections have different weights and masses. For example, a mountain root may be missing and replaced by denser mantle. Such a section will have a greater weight and mass. Gravity meters will detect sections like this. Here, buoyancy alone does not hold up the mountain. The crust on both sides is strong enough to do much of the job. On a larger scale, gravity readings adjusted to measurements made at pendulum stations indicate slight lumps and hollows in the Earth's sea level figure. which we call the geoid. Thus, a clearer picture of our planet's irregular shape is emerging. Most of the gravitational effects that man can now measure with his gravity meters originate in the Earth. But beyond these effects, there is a dramatic phenomenon caused by our nearest neighbor in space, the Moon, and to a lesser extent, by the Sun. This phenomenon is the great cycle of tides. One side of the Earth is about 3% nearer the Moon than the other side. Thus, according to Newton's law, masses on the near side are attracted by the Moon about 6% more strongly than masses on the far side. The waters on the near side are pulled out and gathered by the Moon to form a high tide. And since the solid Earth as a whole is nearer the Moon than the waters on the far side, the Moon draws the Earth away from those waters, thus leaving another high tide. The Earth rotates under the tidal humps, and the continents and sea bottoms resist the flow of high water. This friction carries the tidal humps out of line with the Moon. Depending on the Sun's position relative to the Moon, tides caused by the Sun pile up on the high tides caused by the Moon, or fill in the low tides. The gravitational pull of Moon and Sun also affects the Earth's crust and mantle. While the solid Earth is much less deformable than the oceans, sensitive instruments have measured tides in the Earth up to 8 inches at the equator. This rise and fall provides information about the rigidity and strength of the crust. During the International Geophysical Year, measurements like these also helped us understand more about small shifts in the Earth's crust caused by the pull of the Moon and Sun. Ever since man started launching satellites and studying their orbits, which are governed by the gravitational field around Earth, he has been learning new details about his planet's shape as a whole. Studies of orbits have suggested that the gravitational field around our planet fits a slightly raised Arctic and a slightly flattened Antarctic. Man's conception of the way gravitation behaves has been formed almost entirely within the framework of the universe conceived 3 centuries ago by Sir Isaac Newton. Today, as man gets ready to venture far beyond planet Earth, Newton's laws still apply to most of his physical existence, even the motions that he experiences in the strange state of zero gravity. In this free fall, everything happens the way it does in empty space, far removed from massive bodies and their gravitation. On the other hand, to a man in a centrifuge, everything happens the way it would near a massive body with tremendous gravitation. Here, if a man's weight is increased 10 times, we say he is subjected to 10 Gs. Is this force essentially the same as gravity? And is a free fall really the same as the absence of gravity? Classical physics said no. Albert Einstein was the first to say yes. This answer has led 20th century physicists through a series of logical steps to a new concept of the universe. Gravitation is no longer thought of as a force exerted through empty space by one mass on another. Instead, it is regarded as the way a freely moving body takes the shortest path through space-time. A mass curves the space around it, and measurements obey a curved line geometry. the greater the mass, the more extreme a gravitational field it creates. The new concept of gravitation still allows us to drop a ball, build a bridge, and fly a plane as we have done. But where we can study objects moving at speeds near that of light, in the laboratory, or out in boundless space, we find that time stretches, distances shrink, and bodies become heavier. It is difficult to grasp this universe. We can only keep on observing, measuring, and studying gravitation, along with other cosmic forces. Today's scientists ask many questions. Does gravitation weaken with time, or possibly grow stronger? Is gravitation different in different parts of the universe? If tomorrow's scientists can answer questions like these, man will have a far more profound understanding of the way this force brings order on planet Earth and throughout the universe.